And yeah, so let's take a look here. Come on, there we go. So Friday, I said we were going to take a look at some of these. So if I highlight one of these carbons here, let me ask you, that carbon that I just highlighted in yellow, would you guys consider that to be a chiral center, yes or no? Anybody have an idea? And don't be shy. If you think you have it, yeah, Brianna, yeah, I'd say you're right. I see a lot of people nodding, like, yeah, I think that's a chiral center. You're absolutely right, that is a chiral center. Remember, the carbon has to be attached to what? 4 different what? Groups, not 4 different atoms. And we see that that carbon is attached to an oxygen. It's also attached to this hydrogen. And you're like, well, here it's attached to a methylene. Sure, it's attached to a methylene here, but we keep going until we find a point of difference, don't we, right? If we look at this carbon, you can see that this carbon I have highlighted in black is obviously different than this one I have highlighted in green. The one in green is sp3, the one in black is sp2. So those are 2 different pathways, ergo, that is a chiral carbon. Let me try another one. What if I highlighted this one in red? Would you say that's a chiral carbon? Right? I see everybody saying no. No, absolutely not, right? That carbon is attached to 2 methyl groups. Can't be chiral, right? So we'll scratch that one off of there. Let's try one more, and then I'll just kind of highlight them. What about this guy here? Would that be a chiral carbon, the one that I just highlighted in yellow again? Yeah, again, same rationale, right? It's attached to a methyl group. It's attached to a hydrogen. And I think we can all agree that this group is different than this group, right? One has a bunch of rings in it. The other one is just a chain. There you go. So we've identified 2 chiral carbons. Did anybody identify a total of 5? There's a total of 5 chiral centers in this molecule. As you can see, they're all kind of bunched up here. We have 1, 2, 3, 4, 5. Those would be the chiral carbons in the molecule. Great. All right, so that brings me to another question that we didn't finish. This one here, which was for each of the following molecules, describe it as chiral or achiral and determine whether the molecule has an enantiomer. Well, let me introduce you to the topic of meso compounds. And again, this is something that I left out of my slides. I don't know why I did it, but it is in your textbook. And I'll just show you quickly here in the textbook the topic of meso compounds. And so a meso compound is going to be a compound, so listen to me carefully. It's going to have 2 or more, for our class it's usually 2 or more chiral centers. However, since there's a plane of symmetry in the molecule, it's achiral. And the reason why is because if you have 2 chiral centers in a molecule, but they're mirror images, it's like having a 50-50 mixture. It's like having what we call a racemic mixture, so a 50-50 mixture of 2 enantiomers. So think about it. One's going to rotate plane polarized light in one direction to a certain amount, and the other one's going to do the exact opposite. So what's the net effect? They cancel each other out. And so, yes, there's chiral centers in it. So it's kind of weird, right? You have chiral centers in a molecule, but they cancel each other out on account of a mirror plane in the molecule. And so if we go to this example that I have on the slide, and this is, I would shudder to say this, but I'd say it's kind of a tricky example here. But sometimes students will look at this molecule and they'll say, that's a chiral molecule. Well, it turns out that it isn't a chiral molecule. And let me show you why. If you take this carbon-carbon bond and you rotate it 180 degrees, what you're going to end up with is something that looks like this. So we have 1, 2, 3, 4, 5, 6. Now, this hydroxyl that was on the left-hand side is still on a wedge, but when we rotate it 180 degrees, that hydroxyl that was on a dash, now it becomes a wedge, all right? So we have a wedge like this. And it's not the prettiest drawing in the world, but is there a plane of symmetry in this molecule the way I have it drawn? Sure. And if you're like, do I have to be able to recognize that? Yes, you do. Okay, you have to be able to rotate the bonds and say, hey, you know what? There actually is a plane of symmetry in this molecule. And so I'll zoom in on it and I'll ask you a question about this carbon. And again, there's no trick questions in my class. The carbon that I just highlighted in yellow, is it chiral? Yes or no? Is it attached to 4 different groups? Sure. We would all agree that that is chiral. If I highlight this carbon in green, is that a chiral carbon? Sure. So again, the compound has 2 beautiful chiral centers. Everybody identify them, like, yes, sir, no problem, okay? However, they're enantiomers of each other, aren't they? Right? They're mirror images, but they're trapped inside the same molecule. Does that make sense? Okay? And so, like we said, if you have a chiral compound, it will rotate plane polarized light. But if you have its mirror image, its enantiomer, it rotates plane polarized light in the same amount, but in the opposite direction, yes? So now it's like they're trapped inside the same molecule. So if this one, I'll just spitball a number here. If this one rotates at positive 10 degrees, this one's going to rotate at negative 10 degrees. And so what's the net effect? Is that they cancel each other out. And so we say the molecule is achiral. And there's a term for it. When we have two or more chiral centers in a molecule, but the molecule is achiral overall, what do we call it? Meso. It's a meso compound, okay? I'll try to bring it up again with you today. So a meso compound. Go ahead.
So if it's achiral and it has can't have no plane of symmetry?
Exactly. It can't have a plane of symmetry, right? There's certain exceptions to that, but we don't get into that, okay? All right. There we go. So the topic of meso compounds, okay? And meso compounds do come up a lot in organic chemistry, especially in this class. They come up all the time because we look at small molecules a lot in this class. And so yeah, we run into all kinds of different meso situations. So we went over the Kahn-Ingold pre-log rules, assigning R and S. Come on, you. iPad is slow. Anyhow, and I think we identified some chiral centers, but we didn't identify every chiral center. And so if we take a look at ephedrine, we see that we have two chiral centers in there. And what about the one in yellow? Would that one be R or S? Well, let's review, okay? If you missed class or if you're just like, I just kind of forgot, okay? You can see that this carbon I have highlighted in yellow is attached to 4 different groups. Not 4 different atoms, but 4 different groups. The highest priority, remember we go by atomic number. The highest priority is going to be the oxygen. The lowest priority is always going to be the hydrogen. And lucky for us, the hydrogen is in the back. Okay, that makes it less complex. Now, if I highlight this carbon in green, and if I highlight this carbon in red, which one of those carbons is going to take a higher priority? The one in green or the one in red? I'd say it's the one in red. Okay, and I'll tell you why. So the one in green, going away from the chiral center, is attached to carbon, 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 but the one that's in red is attached to nitrogen, carbon, hydrogen. And so your tiebreaker is going to be the nitrogen because nitrogen has a higher atomic number than carbon. And so we go from 1 to, where's my blue pen? 1 from 2 to 3. Like that, so we're going clockwise. And so what's the chirality? It's going to be, thanks you guys, great. So we identified that one. Let's do the next one. Again, lucky for us, the lowest priority group, the hydrogen, is going to be in the back. It's going to be group number 4. The nitrogen is obviously going to be group number 1, right? Because we have 2 carbons. But if you look at this carbon here, this is attached to 3 measly hydrogen atoms, whereas this one is attached to oxygen, carbon, hydrogen. Again, going away from the chiral center. This is our tiebreaker. And so we have 1, 4, 3, and 2. So we're going 1, 2, 3. And so the chirality would be S because we're going counterclockwise. Did somebody have a question about that one? No? Okay, so this one would be S. There you go. All right, let's try another one. Look at that, an anti-tumor agent isolated from marine organisms. If you've ever wondered, where do they come up with these ideas, for these anti-cancer drugs or the different cardiovascular drugs and stuff? A lot of them come from natural products. I'm glad I never did that, okay? It doesn't sound like excitement to me, but when I was a graduate student, there was a lab upstairs, and I remember they were fermenting grapefruit juice in this giant carboy, and they were isolating different compounds from it. Not my cup of tea, anyhow. But they would elucidate these different structures. Anyhow, so if we take a look at this one here, our highest priority group is going to be the chlorine, okay? The second, so if we look at this one here, it's attached to chlorine, carbon, carbon going away. This one here is attached to bromine, hydrogen, hydrogen. And this one here is attached to carbon, hydrogen, hydrogen. And so we have 1, we have 2, we have 3. Like that. Does that make sense to everybody? Everybody else? Go ahead.
So why wouldn't the bromine be first? Is it just because the carbon?
Because the carbon isn't attached directly to it, right? It's attached to this carbon, right? And chlorine has a higher atomic number. So something that Eric was bringing up last class is he said, could you imagine yourself behind the board, right? What you said, right? Just imagine. Some people are able to do that, okay? Some people struggle with it. But for this one here, we see the lowest priority group is this methylene here. You with me on that? So the way you're going to do it is kind of like what we did with the Newman projection, where you're going to imagine your eyeball is down here and you're looking down like this, right? So what are you going to see when you do that? And I don't have a lot of space here, but what you're going to see is you're going to see the chlorine is going to be up here, right? The CH2Br is going to be here, and then you've got all the other spinach up here. And so you have 1, 2, and then 3 is that group with the double bond and the chlorine on it, right? So you're going like this, so you're going counterclockwise, which is going to be S. Does that make sense to everybody? Okay, that's what I think is the easiest way to do it. Now, I'm going to go over this very quickly with you guys. But somebody came to my office and they said, okay, what if I do the old switcheroo, right? What if I switch 2 groups? So listen to me very carefully. I'll even put my pencil down. They said, what if I switch 2 groups? Can I do that? And I said, yes, you can switch 2 groups, but if you do that, what happens? It's going to invert the stereochemistry. R would become S and S would become R, okay? Now, there's another thing you can do. If you invert 2 groups and then you invert the other 2 groups, then it goes back to being the original molecule, okay? And I always go over this in class, and one of my students who's actually in medical school right now, he's going to graduate next year. I remember he was studying for the MCAT, and he showed up in my office, and he said, Mr. Dion, did you know that if you swap 2 groups, it ends up being the same molecule? I said, yes, I do, G. I taught you that in class. It's like, oh, sorry. Yeah. Anyhow, so make sure we cover that rule in class. Anyhow, for the other chiral center, did anybody get a chirality for this guy? I'll throw it to you guys. You guys all did it last night, right? Or this morning when you woke up at 5, right? Like, as long as you have no follow-up questions, absolutely. All right, so we have our hydrogen coming out in front. All right, so this is 4, this is 1, this is 2, and this is 3, right? So we have 1, 2, 3. We're going counterclockwise, which would be S, but the lowest priority group is coming out in front of us. And so this stereocenter would be R. Everybody good with me on that? All right, rocking and rolling. There you go. Hey, that's great. You know, I see a lot of people being like, yeah, I can do this. Absolutely. You know, there's only one choice or the other, right? So even if you guess, you still get a 50-50 chance of getting it right. But you don't want to do that, of course, right? I'm glad you guys are giving me a funny look when I said that. Good. All right, so we went over Fisher projections. We went over the rules for what you can do with the Fisher projection, but I don't think that we, we didn't assign the chirality at these chiral centers here, did we? So let's look at this compound. So this is just a little more practice on the old R and S here. So with this compound on the far left, we figured out that it was an S compound. What about this guy here? I'll throw it out to you guys. Anybody have an idea about this one? Would it be R or S? There's 1 chiral carbon. It would be an R compound, isn't it, right? So the nitrogen takes highest priority. This is going to take second highest. This would take third highest. Obviously, the hydrogen is last. But is the hydrogen on a dash or a wedge when it's horizontal? It's on a wedge, right? It's coming out towards you. And so we don't want that. And so whatever we read it as, we're going to switch it. And so if we go from 1 to 2 to 3 counterclockwise, that's S, but we know it's not an S compound. It's an R compound, like that. Now, just to go over the last one a little bit quicker. Okay, we'll go a little bit faster on this one. I'll do the top one in red. This carbon here, we have 1, we have 4, then we have 3, and we have 2. Do I have this right? No, that's not right. 1, 2. There we go. 3, like that. Is that better? I think that's more reasonable. So we're going clockwise, which is R. The hydrogen is horizontal, so we switch it. So this is an S stereocenter. So we'll just erase this, and we'll say this is S on the top one. What did you guys get for the bottom one? We'll do that one in blue. Anybody get an answer for the bottom one? S as well, right? So we have, this is going to be the loser, lowest priority. This is going to be 1. This will be 2. This will be 3. So we're going from 1 to 2 to 3, which is clockwise, which would be R. But the hydrogen is horizontal. And so, therefore, this is going to be another S stereocenter. So S and S. What do you think about that? There we go. I think we did that pretty quickly. So that's great. So it seems like we're pretty rock solid on our Kahn-Ingold prelog rules. we didn't finish this one here. Go ahead.
So on the last slide,
Yeah.
you're saying, I kept hearing the hydrogen's horizontal, so you flip it. Is that the general rule you want to follow?
Generally speaking, yeah, because hydrogen has the lowest atomic number. So if it's horizontal, it's by definition on a wedge, so you're going to have to flip it. Yep. Yep. Absolutely. All right. Come on, you. All right. And then this one here, we went over this skill builder a little bit last class where I said you kind of take yourself here and you put yourself at the perspective. So on carbon number 2, you would view this hydroxyl from the bottom, right? Carbon number 3, you would view that hydroxyl from the top. Carbon 4, you would view from the bottom. So if I just look at carbon number 2, okay, so if I do carbon number 2, however, I think my little guy is backwards here with this one, so maybe I'll redraw him because we want to put our head by the most oxidized carbon. So I'll do something like this. There we go. That's not exactly the way he had it, but something like this, right? You want to put your head near carbon 1, right? So if you're looking down there, which side is the hydroxyl on? Come on, you. Which side is the hydroxyl on carbon number 2? Well, you're looking at it from the bottom, right? It's on a wedge, so it's going to be on your left-hand side, okay? So we'll pencil this guy at carbon number 2 on the left-hand side. Therefore, the hydrogen must be on the right-hand side. If we move our little dude up here for carbon number 3, he's, again, not oriented in the right way, but anyhow, if you turn yourself like this, okay, if you're looking at it, it's on a wedge, and so it's going to be on your right-hand side. Does everybody follow me on that? Good. So it's going to be on your right-hand side. Excuse me. And then again, for the last one, you move your little man down here, okay? So he's looking at the bottom like this, right? You can imagine yourself laying down on the floor. You're looking upwards like this. It's on a dash, so it's going into the page, and so it's on the right-hand side again. Oops. And there you have it. Give me a thumbs up if you can do that. Yes? Because I made a question up like this last night, okay? I was like using my ChemDraw, labeling all the carbons and everything. I gave you the skeleton, I think, or maybe I didn't, or I just said, fill out the draw what the Fisher projection would look like, okay? So there you go. I told you one question that's on the quiz already. Is draw a Fisher projection of one of these, something like one of these. Cool. All right, let's keep going. All righty. So we did optical activity. So now we're going to kind of kick it off this morning here, reviewing our stereoisomeric relationships. Okay, going right back to the beginning of the course, and even back in your days of general chemistry, you would have learned constitutional isomers. Again, the ubiquitous example is C2H6O, or I said it could be ethanol, or it could be dimethyl ether. Then you and I started talking about stereoisomers, and we said, well, if you have two mirror images that are not superimposable, like the human hands, what do we call those? Starts with E? Enantiomers. Okay, so those are enantiomers, which are non-superimposable mirror images. Stereoisomers that are mirror images. If you want to write non-superimposable mirror images, okay, that's totally fine. However, what if we have two molecules that have the same connectivity, have a different arrangement of the atoms in space, but are not mirror images? Well, what do we call those? They're obviously stereoisomers. They're a new class of stereoisomer that we call a diastereomer. And so our definition of diastereomer is just a stereoisomer that is not a mirror image, okay? Now, diastereomers may be chiral or achiral. Some chiral centers are inverted. They're not mirror images. Cis-trans isomers are going to be diastereomers. You can remember that. If anytime I give you two compounds that have the same connectivity, one is cis, one is trans, what's their relationship? Diastereomers, done, okay? Whether it's on a ring or whether it's around a double bond. Cool? So cis-trans stereoisomerism is going to be diastereoisomerism. And so this is kind of where we left off last class. As I said, if you had cis-2-butene, trans-2-butene, again, I know I've gone over this with you before. They're both CH3, right? CH, double bond, CH, CH3. They have the same connectivity, but they're not the same compound, are they? Right? They're stereoisomers. Okay, they have a different arrangement of the atoms in space. One goes like this. If I trace the carbon skeleton, the other one goes like this. And so, unlike enantiomers, which are going to stack up the exact same way, and they're going to have the same physical properties, same melting point, same boiling point, same refractive index, same density, same IR, same NMR, okay? Well, diastereomers are going to have different physical properties because they're going to stack different ways, right? They're going to organize themselves different ways in a pure sample. And so if we take a look at these examples here, okay, it says consider cyclohexane with 3 substituents. And so if we just focus in on this molecule here, we'll start here, okay? We've got a cyclohexane that has a hydroxyl group, a methyl group, and a chlorine. Now let's say I gave you this compound on a quiz, and I said, draw me the enantiomer of this compound. What would your strategy be? What did I tell you last class? If you want to draw an enantiomer, you change every wedge to a dash and every dash to a wedge. Done. Don't question it, okay? If it's a wedge, turn it into a dash. If it's a dash, turn it into a wedge. Thus, we can see the relationship between these two compounds is what? What's the relationship between these two compounds? Go ahead, Ren, say it loud.
Cis-trans.
They're not cis-trans because cis-trans has to have only 2 substituents. What would they be? I've changed every wedge to a dash, thus they must be enantiomers of each other, right? These are enantiomers. Good. So enantiomers, I'll just put En for enantiomers. Let's try it again. If I look at these 2 compounds here, we'll do it until we get it. What's the relationship between these 2 compounds in this green box? They're enantiomers, right? Every dash is changed to a wedge. Every wedge is changed to a dash. So again, this is a pair of enantiomers, okay? What about these 2? What's the relationship between these 2 guys? They're enantiomers, right? Every wedge is flipped to a dash. Every dash is flipped to a wedge. And you're like, yeah, also, Mr. Dion, you're not mentioning this. Every R is changed to an S, and every S gets changed to an R. I'd say, absolutely, right? Because if you invert a stereocenter, R becomes S or S becomes R. Are you with me? So right, Micah? You don't even have to see the structure. All you have to do is look at this and say every R is changed to an S and every S is changed to an R. Ergo, they must be enantiomers. Okay, so now you're getting it. You see how every single one of these boxes, there's a reason he put all these in green boxes, okay? It's just because he's showing you that this molecule has 3 stereocenters. And the way we predict the number of stereoisomers that you can have is 2 to the power of n, where n is equal to the number of chiral centers. Chiral centers. And so if we take 2 to the power of 3, it gives us 8. How many stereoisomers are on this page? 8, right? You see, I see you smiling. Why? Because it's all starting to come together. Just give me 1 second. So we end up with 4 pairs of enantiomers in this case. Go ahead.
So I remember in the textbook they were saying about the 2N, they also said something about the mesoisomers.
Yeah, we're going to talk about meso compounds. None of these are meso compounds because for a meso compound, you have to have a plane of symmetry in the molecule.
But like subtracted the number, right?
Yes, if we have a meso compound, we're going to have less than the predicted number of stereoisomers. Yes, absolutely. We'll get to that in just a second, okay? So now we've agreed, we've got 3 stereocenters in the molecule. The way you predict the maximum number of stereoisomers is going to be 2 to the power of, however many chiral centers there are. 2 to the power of 3 is 8. Hey, lo and behold, we have 8 different stereoisomers, 4 pairs of enantiomers. Give me a thumbs up if you're with me on that. Okay, I know it's a Friday morning. You're like, it's been a long week, Mr. Dion. There's a lot to tackle here. I totally get that. Now, we could pick any one of these compounds at random. I'll pick this one. Okay, I picked this one. This is the one. I closed my eyes and I came to this compound. Now, barring its enantiomer, which is in the green box with it, I want you to tell me, if I was to pick, what's the relationship between this guy and this guy? Are they stereoisomers of each other? Yes. Are they enantiomers? Therefore, they are diastereomers. Exactly. What's the relationship between this guy and this guy? They're diastereomers again, right? It's the same old drill. They're stereoisomers, but they're not enantiomers. The enantiomer is the other one in the green box, right? So you can see that that compound, I have the blue circle around, it has 1 enantiomer, and it has 1, 2, 3, 4, 5, flick, right? It has all these different diastereomers, yes? And so you're like, well, you could have, the reason I closed my eyes was for illustrative purposes, right? I could have picked any one of these compounds on here, right? They all have what? 1 enantiomer and 6 diastereomers, yes? Is that neat or what? And again, I know you guys are all very astute. You know, one thing I've learned about teaching organic chemistry is that my students are very quick. And I'm sure you all noticed while I was yammering on, again, what I was saying. You're like, look, you don't even need the structures, Mr. Dion. Stop wasting our time. 1R, 1S, 2R, 2S, 3S, 3R. All you have to do is invert every single chiral center from an R to an S. You get an enantiomer. So if I changed only 2 of them, or just one of them, what do I have? Diastereomers, because they're stereoisomers, obviously, and they're not enantiomers, ergo they are diastereomers, okay? Does that make sense, though? There is a logic to it. Do you have to think about it a little bit? Of course, okay? If you're sitting there going, I'm going to have to go home and study, you know what I would say? You are a normal person. I would say you are a normal person. You're like, I'll never need to look at this again. I would love to shake your hand. I'd like, I need to learn from you, I guess. Anyhow, so there are 3 stereocenters here. We have a maximum number of stereoisomers of being 2 to the power of 3, which is 8. Consider the relationship. We have 4 pairs of enantiomers. If you have 2 stereoisomers and they're not enantiomers, they must be what again? Starts with D, ends with I-stereomer. That's right, diastereomers. All right, I know you guys probably think I'm silly sometimes, but anyhow. Okay, so now if you take a look at a molecule like cholesterol, I mean, hella, is that still a thing? I mean, there's a lot of chiral center. No, it's not a thing? Okay, I'm going to stop saying it then. Thanks, Heidi. Heidi's like, it's not a thing anymore. Get with the program. All right, but we have a lot of chiral centers. So if you're looking at cholesterol and saying, well, you just told me the maximum number of stereoisomers is 2 to the power of n, how many stereoisomers can I have? So let's see. I've got a chiral center here. I've got one here, 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 and here. That's 1, 2, 3, 4, 5, 6, 7, 8. So how many possible stereoisomers can I have? It's 2 to the power of 8, which is 256 possible stereoisomers. Cholesterol has 1 enantiomer, right? 1 enantiomer is going to have 254 diastereomers on it. And the human body can make this thing, right? So yeah, it's pretty amazing synthesis. Anyhow, there you go. All right, I told my wife, I said, as a graduate student in an industry, I would try to make all these molecules. I was sweating and suffering to make a molecule that had a molar mass of 550 grams per mole. And I said, you took, in your womb and just like pH of 7 and came out with a whole human being. Like, I can't compete with that. This is pretty amazing synthesis you're doing there. Anyhow, so going back to the idea of a meso compound, I guess I missed it. But anyhow, if we take a look at this compound here, okay, how many chiral centers are in this molecule? I'll zoom in it for you. It's no trick question. How many? Everybody got 2, right? Everybody said, yep, Mr. Dion, that is a chiral center. Yes, and that is a chiral center. And I would say absolutely, okay? 2 chiral centers. So, Kevin? Yeah, so going back to Kevin's point, Kevin said, okay, going off of what you said on the last slide, the maximum number of stereoisomers that we could have would be 2 to the power of 2, which is what? 2 squared is 4, right? So we have 2 to the power of n is equal to 2, 2 squared is equal to 4. Now, we see that in the green box, we have the compound in the yellow circle, and then we change the wedge to a dash, the dash to a wedge, so we have a pair of enantiomers. But if you look at these 2 here, you see that this compound and this compound are diastereomers, aren't they? Right? You only inverted 1 chiral center. However, and this is what Kevin was asking me about, he said, yeah, but what about the relationship between these 2 compounds? Does everybody see that these 2 compounds are identical? They are identical, aren't they? Okay? And if you're like, am I going to be expected to recognize this? Yes. Okay, you're expected to recognize this. What kind of compound is this? It's a compound that has chiral centers in it, but there's a plane of symmetry in the molecule which renders it achiral. Achiral doesn't mean there's no chiral centers. Achiral means it doesn't rotate plane polarized light. Yes, there's 2 chiral centers, but they cancel each other out. And so what do we call that kind of compound? A meso compound, right? Exactly. So this is a meso compound. So what Kevin was getting at is he said, well, the book said sometimes you can use that formula and there's actually less stereoisomers than you would think. You'd say, oh, 4. I'll start trying to draw 4. But there isn't 4. There's only 3, okay? And so I've asked this on quizzes before. Well, I'll give you a compound and I'll say, draw all the stereoisomers. And if there's only 3, I only expect you to draw 3. I don't expect you to draw, this meso compound twice. That would be incorrect. Cool? There you go. So meso compounds. So overall, what's our conclusion? Oh, I don't know. Overall, the presence or absence of rotational symmetry, okay, so if we rotate a molecule, is irrelevant to chirality. A compound that has a plane of symmetry is going to be achiral, right? We saw that with meso compounds. Despite the presence of chiral centers, if you've got a mirror plane in there, it's an achiral compound. It's not going to rotate plane polarized light. However, a compound without a plane of symmetry will usually be chiral. There are some exceptions. Compounds with inversion centers is an example of something where where that rule doesn't apply. We will not look at compounds that have inversion centers. I know in the textbook he brings up one example. He shows you an example with an inversion center. I don't know if I have it hauled up right now. I don't think I do. Let me see here. No, he used to go on about it in the old textbook. I don't even know if he does anymore, so don't worry about that. The problems that we're going to be interested in are the kind of things that I showed you in class, okay? Don't worry about learning extra stuff. All right, let's see if we can identify the following pairs of compounds as enantiomers or diastereomers. We'll do this very quickly. We start with these 2 guys here. You see that at the top, the wedge has been converted to a dash, and at the bottom, the dash has been converted to a wedge. Ergo, they are enantiomers. Thanks. Enantiomers. Okay, what about these 2 compounds right here? What would these guys be? They're diastereomers, right? Only one of the stereocenters has been inverted, so these would be diastereomers. Okay, now, for these 2 compounds, it's a little trickier, right? Because you see they're not written in the same perspective. You see that the carbon chain here is zigging and zagging, right? But here it's going like this. There's 2 ways you can solve this. Okay, there's 2 ways to do it because they do have the same connectivity, yes? Okay, but they have maybe a different range of atoms in space, maybe not, okay? The 2 ways to do it, number 1 would be to rotate this bond and then put this methyl group in the same plane, okay, to do that. I've taught this class a long time. I feel like my students are so good, are so powerful at designating chiral centers as R and S that I like to say that's maybe a better mode of attack. They both work. They both work. If you like the other way, by all means, go ahead and do it. But what I want to do is assign these chiral centers as being R or S. Now, I'm not a guy about racing or anything like that or being how fast we can go. But let's see how fast we can go. Here we have 1, 2, 3. Hydrogens in the back. It's going clockwise. Therefore, this chiral center is R. If we go to the second chiral center here, we have 1, we have 2, we have 3. The chiral center is in the back. Therefore, we have R. So this is RR. All right, can I give you guys a second to try to suss out those other 2 chiral centers? This one and this one. I'll give you guys a second to give it the old college try. For the chiral center on the left. Anybody? R, right? We're going from 1 to 2 to 3. The hydrogen's in the back, so this would be R. What'd you guys get for the second one? S? Yeah, me too. So we go from 1 to 2 to 3. The hydrogen's in the back. It's going counterclockwise. And so it's S. Now, if we were to compare R, R, and S, S, those would be enantiomers of each other, right? Because we inverted everything. But if we compare RR versus RS, we've only inverted one stereocenter, ergo they must be diastereomers. There you go. Feeling good about it? Good. Diastereomers. Was that a comment of joy or good? Okay, all right, good. What about these 2 here? I'll zoom out. What about these 2 Fisher projections? There's 3 chiral centers in each molecule. So we have one here, here, and here. You look at the one on the top, it's inverted. You look at the second one, it's the same. And if you look at the third one, it's inverted. So they're not enantiomers because they're not all inverted, right, Nicole? So what must they be? Diastereomers, exactly. Thanks, you guys. Great. Diastereomers. Beautiful. Neat? Did anybody read the textbook before coming to class? Yeah, I hope this is clearing up anything that you're like, oh, it's a little bit confusing when you read the textbook. I hope I'm clearing it up for you. Good. Okay, so Kevin, this is your question that you were talking about, okay? It says, draw all possible stereoisomers for these compounds. Each possible stereoisomer should only be drawn one time. You know, it's like the student, I know you guys don't do this, but sometimes you'll ask a question on an exam, and a person will write down every possible answer, like, you know, the right answer must be in there. No, it's like, you got to give me the answer, okay? So that's why usually I'll say circle, you know, or something like that. Okay, how many chiral centers are in this guy here? How many chiral carbons are in here? Attached to, there's 2 of them, right? Absolutely. We have a chiral center here. We have a chiral center here. We use our little formula, 2 to the power of 2 equals 4. And so we can start by drawing, I'll put a dash here, I'll put a wedge here, and then I'm going to draw its enantiomer. I'm going to change that dash to a wedge, and I'll change this wedge to a dash, and so we have a pair of enantiomers. You with me so far? Okay. Could somebody describe another stereoisomer that I should be drawing that I've left out? So I've got one where they're like this, I've got one where they're like this, one where they're both on the same side. Yeah, where they're cis. Let's do that, okay? So I'm going to draw 2 wedges, just that's what I'm feeling right now. Just 2 wedges like that. Now, if I was to say 4 stereoisomers, just watch me. Uh-oh. What I just did there in red, is that right? No, what did I do? I just redrew the previous compound, didn't I, right? So this is technically not correct because it says only draw them once, and this is what kind of compound? A meso compound. A meso compound. Any questions? It's a lot of talking today, okay? I take that to be good talking, like, yes, I get it, okay? So, any questions about that? No? Okay. I'm going to skip the next 2 just in the interest of time. I want to make sure we get through everything, and it's already 8:42, so I want to make sure we get through everything. This slide here, I just put this on just as to illustrate a point. So you see here we have the 2 enantiomers of ibuprofen, R and S. And so we have enantiomers. Okay, so we have R and S. What do you notice? Their melting points are identical. Their water solubility is identical. Their ethanol solubility is identical. Furthermore, their IR is going to be identical. Their mass spec is going to be identical. When we look at NMR, those are going to be identical. What else? Density is going to be identical. Flash point is going to be identical. Go. What's the only thing that's different between the 2? The way they rotate plane polarized light. One rotates at positive 57 degrees. The other one rotates at negative 57 degrees. Yes, it's difficult to distinguish between enantiomers. What's the relationship between cis and trans stilbene, though? They're not enantiomers. What are they? They are diastereomers, right? Now, if you look at those 2, stereomers, look at this. Melting point 5 degrees Celsius, melting point 124 degrees Celsius. You guys have taken a melting point using the melt temp probably. How long would it take you to distinguish between those 2? Warm it up, throw the 2 vials, right? Throw the 2 samples in, one poof, is melted in 2 seconds, like you turn your head, like that's gone, right? And the other one's still intact. You're like, well, I guess I know which is which. That didn't take very long. You're with, cool? Yeah, there you go. And then you see all these different sugars here. We've got xylose, lysose, arabinose, ribose, and you see, what are they? They're diastereomers of each other. They all have different optical rotations. They all have different melting points. Pretty neat, huh? There you go. So now you know a little bit more about enantiomers and diastereomers. Cool. Let's talk about E and Z for a few minutes. So you guys know the difference between cis and trans, right? What if you have these 2 alkenes? Are these 2 alkenes identical to each other? Are they the same? It's not a trick question. No, they're not the same. Look, if I follow the fluorine to the oxygen, look, here the fluorine to the oxygen goes like this. Here it goes like that. You with me? These are certainly not the same compound. They have the same connectivity, right? The double bonded carbons have a methyl and or ethyl and a fluorine, and then that methoxy group on them. But they're stereoisomers. Give me a thumbs up if you agree they're stereoisomers. Okay. Turns out we can't use cis or trans in this particular case. Cis and trans is reserved for when we have two groups that are identical. Like if you have two hydrogens, two methyl groups, two chlorines, right? Two groups that are identical on the same side or on opposite sides. Here, you have 4 different groups on the 2 carbons. Yes? If you don't believe me, look at these 2 carbons. We have this carbon in blue, this carbon in red. On the carbon in blue, we have an ethyl and a fluorine. On the carbon in red, we have a hydrogen and a methoxy group. Ethyl, fluorine, hydrogen, methoxy. These are 4 different groups. Good news is this. You guys remember using the Kahn-Ingold-Prelog rules that we use for designating RNS? Assigning a double bond as being E or Z, you use the exact same rules. Okay, watch. What we're going to do is we're going to start with that carbon I had highlighted in blue, and I want you to look at the 2 atoms it's attached to. It's attached to a fluorine, and it's also attached to this carbon. Which one of those groups is higher priority, the fluorine or the carbon? The fluorine, right? Fluorine has highest priority, and so, I don't know, I'll put a box around it. Okay, we'll put a box around it like this. Now, on the other carbon, I'll highlight this carbon in red. It's got a measly old hydrogen attached to it, and it's got an oxygen attached to it. Which one's higher priority? The oxygen or the hydrogen? It is the oxygen. Good, so we'll put a box around this. Since they're on the same side, we say it's Z, which is zusammen. Okay, does that work? Zusammen is together, right? Together. So zusammen, it's just, I've taught this class for a long time. I told you I took German class, but anyhow, my students will say the same side. Okay, the same side. Okay, they have all kinds of funny ways of remembering these things. And then for the other one, we see the highest priority group again is the fluorine, and here we have the methoxy, but we say they're on opposite sides, and so for that we use E, which stands for entgegen, right? Okay. Or my students like to say opposite. Okay, they're opposite of each other. Again, these are things my students have taught me over the years. So, what did we learn? The only time you're allowed to use cis and trans is when you have 2 groups that are identical to each other. Otherwise, we use E and Z. Now, if you're astute, which I know you all are, you're saying, yeah, but if I have a cis-2-butene, couldn't I call it Z-2-butene as well? The answer is yes, you could. So listen to me carefully. If you have a compound that is cis or trans, a double bond, you can use E and Z. Generally speaking, if you have 2 groups that are identical, we like to use cis and trans, but E and Z are still correct. However, if you have a compound that's E and Z, usually you can't call it cis or trans. Now, a question I remember being asked when I was studying this, when I was where you are, I remember there being a question on our exam, and it said, can a double bond be cis and E at the same time? Or could a double bond be trans and Z at the same time? Things to ponder. Things to ponder. Anyhow, we'll come back to that maybe later on. So, I've gone over the rules with you. If they're on the same side, we use Z. If they're on opposite sides, we use E. So, E and Z. All right, so we've gone over that. Let's see if we can assign some beautiful double bonds as being entgegen or zusammen. All right. I told you about my experience in second year German, where the instructor said I was the worst student in the class, you know. Yeah. It's like sweating, you know. All right, so I'll give you guys a second for the first one. We'll do the first one on the left. Did you guys get an answer for that one? Is that one zusammen or opposite or? Okay, let's take a look. We highlight this carbon in red, and then we'll highlight this carbon in blue. I think the carbon in blue is easier because it has a hydrogen attached to one of the carbons. So thus, obviously, this, let me get the yellow highlighter. This is obviously a higher priority group, this group here. But I look on the other side, I have an isopropyl and I have a butyl. If we make our little laundry list, this carbon is attached to carbon, carbon, hydrogen, but this carbon is attached to carbon, hydrogen, hydrogen. Thus, our tiebreaker is going to be here. And so the higher priority group is going to be the isopropyl group. And so this would be what kind of compound? E, because they're opposite, right? E. Let's try the next one. On the carbon that I'm highlighting in blue, I think it's, I don't want to say anything's obvious in organic chemistry, but fluorine has a higher atomic number than carbon. Then we've got a tert-butyl group here. So this carbon is attached to carbon, 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 whereas this carbon is attached to oxygen, hydrogen, hydrogen. My tiebreaker is here. And so my higher priority group is going to be all this spinach here. Thus, what kind of compound is this? Z. All right. And the last one, we'll do it really quickly. It's going to be a Z compound, right? The chlorine is higher priority than the carbon, and then the carbon is higher priority than the proton. So there we go. And there we go. How do you feel about that now? Now you're like, hey, I learned a few things today. I learned E and Z. I think I can do that. Great. You learned about diastereomers. You learned that how to predict the total number of stereoisomers. You learned what a meso compound is. You learned that why it's achiral, even though it has chiral centers in it, right? They cancel each other out. A whole bunch of cool stuff that we've covered today. What about mixtures of enantiomers? So a little bit about synthesis. Once we get to chapter 7, that's when we're going to start making compounds. We're going to learn how to do reactions, make an alkyl halide, and elimination reactions, substitution reactions, SN1, SN2. But if you've ever wondered, like, what's the whole point of this? Do you guys ever think about that? Like, what's the point of organic chemistry? You know, I guess different people have different opinions, but the right opinion is mine. And my opinion is that what's organic chemistry for? It's to discover new medicines, to extend and enhance human lives. And, you know, people, myself included, sometimes will pine for the old days, and I'll think, boy, when I was Jackson's age, boy, that was the golden time, you know, in the 90s, you know, before the cell phone. My wife and I were talking about that the other day, and I said, would you want to go back to not having cell phones? And I said, I think we'd be so depressed, you know, I don't think we could handle it. Like, our brains are so well adjusted to this. But anyhow, my point is this, is that, you know, when people say there's been no advances in medicine, which I know you guys don't say that stuff, you know, you're scientists, but, you know, I don't think there's anybody in this room who'd say, I would like to go back 30 years, just 30 years ago to 1996 and have the same medicines that were available then, right? You with me on that? You know, and not to be traumatic. Did I tell you the story about my friend in the 3rd grade and his mom coming out? Okay, and again, I don't want to be a downer or something. There's always a positive side to my stories, or at least I try to. But when I was in the 3rd grade, I went over to my buddy's house. We were like listening to Michael Jackson, you know, listening to Thriller or whatever. And I remember him saying like, hold on, I got to take Mom to the bathroom. And I'm like, did I tell you about that? Yeah? And he's like, I got to take Mom to the bathroom. And I'm like, Mom to the bathroom? And this little lady came out in a house coat. She was not much older than you guys. She was maybe 30, you know, and that was 3rd grade. And by 4th grade, she was gone. And, you know, and she had breast cancer. And, you know, am I saying that there's a 100% chance she'd be alive now? No, but I'd say there's a very good chance she would be alive if she had had that now. Because of what? Because of the medicines that have been discovered since then. And one of the biggest developments in treatment of, you know, cancer of the breast was the discovery of Taxol. Have you guys ever heard of Taxol and Taxotere, right? And where did that come from? It came from the bark of the Pacific yew tree. And then they said, well, we can't chop down all the trees and take all the bark, then they'll all be dead, right? So then they found a compound that was close to it in the needles of the tree, and the scientists found, organic chemists found a way to take that and to convert it into the cancer drug, and, you know, and then they eventually found a way to make it in the lab. And so it saved a lot of lives. I could go on and on. But most drugs that you encounter, if you guys took a look at that list of 200 small molecules, remember we looked at it one day when we were talking about functional groups. Now that you know about chiral centers, go back and look through it, and you'll notice that most of those compounds have a chiral center. Not all, but most of them do. And in this class, we don't even look at chiral synthesis. So there's synthesis, and then there's chiral synthesis, which is making something that's enantiopure. It's only one stereoisomer. Very difficult to do. Okay, we do it. Okay, scientists do it. So when you do a synthesis and you end up with a 50-50 mixture of enantiomers, it's tough because they have the same physical properties. You can't separate them on a TLC plate. They have the same IR, right? And you're like, well, then how do you separate one from the other? Because our bodies are chiral. It's a great question, and I'll address that before we leave here today. But again, why do we learn all this stuff, right? To me, it's what I'm passionate about or what I did for a long time was try to discover new medicine. So I really think that's one of the best things about organic chemistry, right? Discovering new drugs to save people's lives. Anyhow, I'll tell you another story about that some other day. Remind me, I can tell you some testimonials and stuff from people that came to companies I worked for. But anyhow, what's optical inactivity? We saw a meso compound, right? And we said it was achiral. I said even though it's got chiral centers, it doesn't rotate plane polarized light. Optical activity occurs either when a compound is achiral. Sure, that's true, but what if you have two enantiomers in a mixture and they're 50-50, right? You could have all kinds of chiral centers in it. Think about it. Remember cholesterol with those achiral centers? If you take cholesterol, pure cholesterol, it's going to rotate plane polarized light because it's chiral, yes? If you put 50% cholesterol and 50% it's an enantiomer, it's not going to do anything. Are you with me on that? It's a 50-50 mixture. We call that a racemic mixture, a 50-50 mixture of two stereoisomers. Again, we are only going to look at achiral synthesis in this class, but if you're wondering, how do you separate those two, RNS, 2-chlorobutane? That's a great question. And again, I'll try to address that later on, or right now. Sorry, I have it on this slide. So how do we separate compounds that differ from one another? So how do we separate a 50-50 mixture of RNS? How do you do it? There's a few ways, and believe you, Mr. Dion's not an expert at separating compounds. I'm more of an expert at synthesizing the compound enantiopure. But one thing you can do is distillation. This is for compounds that have different physical properties, is we use distillation or recrystallization. Have you guys recrystallized something in the lab yet? Yes. Okay, so you know a little bit about recrystallization. However, if you have a racemic mixture, if you have enantiomers, you're not going to be able to distill them to separate them. You're not going to be able to use recrystallization to separate them. And so the first person to resolve enantiomers to separate them was Louis Pasteur in 1847. He resolved the two forms of tartaric acid, so RNS. However, you might laugh at it. You're like, he did it by hand? Yeah, he did it with, who's heard this before? No, I thought you were like, I heard this in biology class. Yeah. Because the two crystals, Eric, he could tell under a microscope, you can see the different shape of the two crystals. They're mirror images. So he literally took tweezers and was like, there's one crystal, examine in this pile. The next crystal in this pile, okay? That's not practical, okay? That is not practical whatsoever. However, he did it. So if you're like, okay, two enantiomers, same physical properties, that sucks, okay? But you told me that diastereomers have different properties, right? They're going to have different IRs, different MS, right? They're going to have different retention factor, right? RF on a TLC plate. So what you can do is you can take a racemic mixture and you treat it with a chiral compound, like is being shown here. Now you take enantiomers and you convert them into diastereomeric salts. And so you're going to be able to separate a pair of diastereomers. Why? Because they're going to behave differently on silica, what have you, okay? And so this is a picture, I think I took it off of the internet somewhere, but chiral chromatography is one way we do it. You guys know the TLC plates that you would have used with Dr. Lakakula, right? And it has silica on it, right? And then you can look at under the ultraviolet light. Well, the idea is this, is that instead of just regular silica gel, is that you use silica gel that's chiral, okay? It's a chiral silica gel, and so diastereomers are going to have different retention factors on it. Anyhow, let's move on. Let's go into section 5.10, which deals with non-superimposable mirror images. I honestly don't think I put any questions on the quiz about this yet. If I did, it would be one question, maybe one question about like a very small question. It's just, you know what, when I took this class, I don't even remember learning this, and they probably taught it and I forgot it. It's something I never thought about a whole lot. Do you guys remember your Newman projections? Like, yes, I do. You asked me a bunch of questions about them on a quiz. You made me draw a bunch of Newman projections. Well, if you have butane, right, 1, 2, 3, 4, and you look down the carbon 2-3 bond, this is a Newman projection, right? We have a gauche effect there between the two methyls. And this is a Newman projection, right? Because we know we have free rotation around this carbon-carbon bond. Now, again, if you look at those two conformations, you see that they're mirror images of each other, aren't they? right? And you're like, yeah, but there's no chiral centers in butane. It's CH3s and CH2s. It's not an achiral molecule. You're 100% correct, okay? But they are enantiomeric, right? They are mirror images of each other. But obviously, this is not a chiral compound because we have free rotation around that carbon-carbon bond. And so we say they're rotamers. So again, they're enantiomeric conformations, but the molecule is not chiral. Now, the one last thing I want to cover with you before we get into some, oh, actually, there's a couple more things. If you take a look at these two forms of cyclohexane here, that would be another example of, you see they're mirror images of each other, even though that's a meso compound, right? That's cis 1,2-dimethyl cyclohexane. And so, yeah, overall there's a plane of symmetry. But again, we can have conformations that are enantiomeric. You know what? I'm not going to ask you about that on the quiz, okay? I'll leave this more as an FYI, okay? I'm thinking about what I'm going to do on the quiz now. I don't have the strength to do it, okay? I don't feel like asking you this. I just don't feel like it. You got enough on your plate already with your E's and your Z's and your mesos and your R's and your S's and your this and that, okay? Another cool thing that I used to skip, but I think it's pertinent for you guys, is, I don't know about you, I did a science degree. I'd say I'm a little bit nerdy, you know, and sometimes I just see something in class and I say, that's interesting, you know, or that's kind of neat. Check this out. See this compound here? You see how there's not a single sp3 hybridized carbon in there? Right? Would you agree? Every carbon in there is sp2 hybridized. Okay, now we're getting very fast at recognizing this. However, the pH stands for phenyl, so it stands for an aromatic ring, okay, attached to something, so that's phenyl. So this is a phosphorus with two phenyl groups attached to it, okay, so it's big, right? This is another phosphorus attached with two phenols. Thus, if you make this model of this compound, since those phenyl groups are so big, you try to rotate it, you try to flip it around that axis. See the arrow, the little arrow spinning, okay? You try to rotate and it can't do it. It won't happen, right? It'll go like this, it'll go up, and it won't do it, right? Are you with me? Right? If you have the mirror image down there, the R, it's the same thing. You try to rotate it to get it to cross over, and it can't. So there's no chiral centers in the molecule. These two compounds, the R and the S binap, they're enantiomers. Why? Because of restricted rotation, because you can't rotate around the bond. It's another type of, you know, stereoisomerism. They're called atrope isomers or atrope isomers, depending on the person. So atrope isomers or atrope isomers is what I call them. They're stereoisomers that would be interchangeable through the rotation of a sigma bond, but they're stuck, okay, just because of the size of the group. You can't rotate it, okay? So therefore, they're enantiomers of each other, and I just wanted to share that with you. I thought you guys might find it, you're like, that's kind of cool. Yeah, you have no sp3 hybridized carbons, but you have a chiral molecule, okay? Cool. All right, and the last thing is allenes. I'll put like one example or two examples of an allene. If you're like, what the heck is this? A carbon with two double bonds? You're blowing my mind, you know? Anyhow, could you guys tell me, no trick questions, what would be the hybridization of that carbon there with two double bonds on it? It would just be sp, right? Two regions of electron density. Yeah, it's sp hybridized. But since it's got two pi bonds coming off of it, you see how those two pi bonds are perpendicular to each other? And obviously there's restricted rotation there, right? We can't rotate a pi bond. And so allenes are compounds that possess two adjacent carbon-carbon double bonds. They may or may not be chiral depending on the substituents you have. So if we have a mirror plane, they're going to be achiral. If we don't have a mirror plane, then they're going to be chiral compounds. The two groups on each end of the allene, if the two groups on each end of the allene are different, it's going to be a chiral compound. And so if you take a look at these two compounds here, you can see they are mirror images and they're not superimposable. Right? If you were to take this one and flip it around and try to put it on top of the other one, you see how this methyl group would end up on this side. And thus, they are enantiomers of each other because they're stereoisomers and they're mirror images. Alrighty. So, based off of that, let's take a look at these molecules, these allenes, and all it's asking us is to determine whether they are chiral or achiral. So what we're looking for here is a plane of symmetry. And it's kind of hard for me to draw a plane of symmetry on some of these. You have to visualize it. But I'll just ask you guys, on the one on the top, is there a plane of symmetry in there? Yes, I would say there is, right? If you imagine, if I had like a samurai sword or something. Achiral. What about the next one? Does that have a plane of symmetry in it? Again, there's no trick questions. Obviously, no, it doesn't, right? There's an ethyl group on one of the carbons and a hydrogen on the other side. Therefore, there is no plane of symmetry there. And so this is going to be a chiral compound. What about the next one? You've got that. Go ahead.
I'm not really understanding the first one, how that's achiral.
So if you take and you chop through here, right, and through all this, right, if you're looking down, if you had your eyeball looking down like this, what are you going to see? You're going to see CH3, and you're going to see this carbon, and you're going to see CH3, double bond, carbon, right? And then you're going to see CH3, like that. And underneath this, there's a hydrogen that's underneath there. So there is a plane of symmetry through the molecule. Does that help? All right. Not the prettiest drawing, but is again, if you were standing on top of it and you went shoo, like that, it would break into two pieces that are identical. Yes? Okay. All right. Now, if we go to the third one, would that be chiral or achiral? Achiral. Or actually, no, this is chiral, sorry, because you have a methyl group here. Oh, hold on. Actually, no, this would be achiral. Right? I need to look at these more carefully, right? Why is this achiral? It's because of this guy. Imagine yourself looking down on it like this, right? You chop it from the top, right? If you were standing, okay, this is why they pay me $3 an hour. If you were standing on top of this, what would you see? You would see the CH3 group, right? CH3, which is symmetrical. Then there's a hydrogen below it, yes? It's underneath, okay? Then you have the double bond, you have this, and then you have this. So there is a plane of symmetry running through the molecule, yes? Imagine yourself standing on top of this carbon. That's what you see looking down. There's a plane of symmetry through the molecule. Excuse me. What about the last one? It's chiral, right? Because of the double bond, yes. So this would be chiral. If you're struggling with these, what I would recommend doing is building a model. If you find it really challenging, if you go to the Science Center with their model kits, you can build these allenes. Okay, let's try a couple more, determining whether a compound is chiral or achiral. Start with this guy here. Is this chiral or achiral? It's going to be a chiral compound, right? It has an enantiomer, right? So this would be chiral. What about this guy here? Is that chiral? No, there's a plane of symmetry in there. There's no carbon that's attached to 4 different groups. Sometimes they try to trick you with wedges and dashes, right? But it's carbon with 2 methyl groups on it, so there's no chirality there. So this is achiral. Achiral. Now with the next 2 compounds, one of them is chiral and one of them is achiral. If I call this one A and I call this one B, could anybody tell me which one is the achiral one? It would be which one? B, right? Because when you rotate this bond, right, if you rotate that 180 degrees, you're going to end up with this, where we have this hydroxyl pointing up, and this hydroxyl is going to be pointing up. What kind of compound is this? Anybody? It's a meso compound, right? Maybe I'll use a dashed line or something. Come on. If I put a dashed line through it, this is meso, and meso is achiral by definition. It's never chiral. If you rotate this bond 180 degrees, you end up with this, where you have the hydroxyl pointing up and this one pointing down. That has an enantiomer, and so it is a chiral compound. So we'll put here, excuse me, chiral, and then here we'll put achiral. Achiral. Good. What about this guy here? I'm sure somebody's been thinking about it. Is there a plane of symmetry in there? Sure. Straight down through the molecule. Okay, there's a plane of symmetry right through here, like this. And so this would be achiral. What about the next compound? Could you draw an enantiomer of that compound? This one here? Sure. So that would be a chiral compound? Sure. Oops. Chiral. What about the next compound? I don't see any plane of symmetry in there. Okay, you could draw an enantiomer, so that would be a chiral compound as well. What about the very last compound? What kind of compound is that, everybody? A meso compound, right? You got two chiral centers, but there's a plane of symmetry going right down the middle of the compound. And so this is meso. So we'll put here meso, therefore achiral. Beautiful. What time is it? It's already 9:11. Jeepers. Okay, for each of the compounds, let's figure out if these are E or Z. So we'll do all four of these. All right, top left-hand corner. I'll give you a second to try to assign all four of them. E or Z for that one? I agree. That is an E compound, right? Could you also call it a trans compound? Yeah, you could call it trans because the two hydrogens are on opposite sides. So we could say E, or technically you could call it trans. What about the one with the methoxy group on it? You've got a hydrogen up here. So what about this guy? It would be Z compound, yeah. What about this guy here? Ethyl group is going to take priority. What about this one? It would be E compound as well. Yep, see, you guys are faster than me at this. And then the last one, we've got a hydrogen down here. So the methyl group is going to take the highest priority. Here we have a carbon that's attached to carbon, carbon, carbon. And here we have a carbon that's attached to oxygen, hydrogen, hydrogen. Well, oxygen wins. And so it's going to be this group and this group. So it's going to be another. What do you think? Not too bad? Yeah, oh, you're smiling. That must mean you like stereochemistry. Good. Makes me happy too. I'm going to skip this one. Let's see here. Draw the enantiomer. We can do that. Let's see. It's 9:13. Let's just try a couple more R and S's. Let's try everybody to assign this one. And we'll get everybody to assign this one before we leave. Okay? Then we can maybe call it a day. Yellow. We got yellow. And we got green. R, is that what you got was R? That's what I got too. So we have 1, we have 4. Then if we go to this carbon is attached to carbon, carbon, hydrogen. This carbon is attached to carbon, hydrogen, hydrogen. And so this would be group 2. Even though the other one has an oxygen in it, right? Don't be fooled. Okay, we follow the Kahn-Ingold-Prelog rules. So we go from 1 to 2 to 3, which would be S, but the lowest priority group is coming out towards us. Thus it is. There you go. What do you think? Not too bad? Is this what, anybody like this chapter more than they like the chapter on infrared spectroscopy? Well, IR's not going away, okay? It's not going away. I got all kinds of... How about a bonus question about some IR? Anybody feeling that? You're down for that? All right, I could